Hello, welcome to the second module on network theory, which is speaking about time domain analysis in RLC circuits. We're going to be discussing what are known as initial conditions, and this apply to circuits which have inductances and capacitances in them. References which have been used mainly are William Haight, Electrical Circuit Analysis, Charles Alexander and Matthew Sadiku, Fundamentals of Electric Circuits, and Ravi Shar Singh. So we are going to be discussing about time domain analysis in RL and RC circuits, initial and final conditions. Okay, so what do you mean by time domain analysis? This mainly applies to circuits which have inductances and capacitances. Now, what is the property of inductance and capacitance, or what are these elements? These are basically energy storage elements. So when you have a network containing such energy storage elements, like the inductor and capacitor, and you have switching from them. So there is some kind of a switch, and this switch is turned on or off, or from one condition to the other. Then the current or the response of the circuit. So the current and the voltage will change from one state to the other. Now, when you are subjecting this network to a switching, and the network has some energy storage elements, then the time taken to change from an initial steady state to the final steady state is called as a transient period. We'll speak more about what is meant by initial steady state and final steady state. So transient period is, as the name says, it is transient, or it dies out after some time, and it is a transition state from one state to the other. Whereas, the output or the response at that time is known as a transient response. It's also called as a natural response. And the response of the network after it reaches a final steady state value is called as a steady state response. So when we are speaking about time domain analysis, we will be understanding what is transient response and steady state response. Now, before we go to
Now, what is an inductor? Inductors are available in different forms in the market. It's basically a coil which can be represented by L, and the coil is represented like this. Now, it is a passive element that stores energy. The voltage across the inductor is given by L into di by dt. Now, we know that the inductor resists abrupt change in the current through it. We'll discuss about this. And there is no voltage across an inductor if the current through it is not changing with time. Or in other words, inductor is a short circuit to DC. So these two things, that the inductor, this is something which we know, that the inductor resists an abrupt change in the current through it. Sudden changes in the current are not supported by an inductor. And the second thing is that it becomes like a short circuit to DC or steady state.
observing the equation, V is equal to L into di by dt. So we understand that the inductor opposes any abrupt change in current. How do you understand this? If the current through the inductor suddenly changes, which implies that dt is equal to 0. Now, if dt is equal to 0, then it implies that V tends to infinity. Now, this is a very high voltage which will occur across the inductor. So, the inductor opposes any sudden changes. So, that is one thing. That is, V cannot be equal to infinity. This is one thing. Second case, that is, if current through the inductor reaches steady state. So, if I becomes constant, that is, or the reaches its steady state value, then that means what? If the current is constant, then di by dt is becoming equal to 0. So di by dt is equal to 0, which implies that voltage is equal to 0. Voltage across the inductor is 0, which again implies that inductor behaves like a short circuit. So this is what we were saying, inductor behaves like a short circuit. So this is why we used to say like a short circuit in this condition. So in DC, that is why we say that the inductor acts like a short circuit to DC. Why? Because DC current is constant, it is not varying like in the case of AC. So if current is constant, then di by dt will be 0 and voltage will be 0, which in other words, it means that inductor behaves like a short circuit to DC or to steady state conditions. Okay. So when we speak about the capacitor is also another passive element, and it's also an energy storage element, which has basically two conducting plates on which charge can be stored, and there is a dielectric in between those. So we can write the expression for, so this is how the capacitor will be, which plus minus minus. So charges on these conducting plates, and there is a dielectric in between. Now the charge can be written as Q is equal to CV, and current hence can be written as current is dQ divided by dt or C into dV by dt. So this is the expression for the current which we have, and by observing this we can see that if there is an instantaneous voltage change, or if when we are speaking about this case, if you want to change the voltage across a capacitor by a finite amount in zero time, it requires an infinite current through the capacitor. So if dt tends to 0, like we have this case, okay, we have I is equal to C dV divided by dt. Now, as we said, if dt tends to 0, then which implies that dv by dt tends to infinity, or I tends to infinity. So this is not possible. So the capacitor opposes any instantaneous change in voltage. That is one. So which means that if the voltage across a capacitor initially was 0, then immediately when there is a sudden change, the voltage cannot immediately change. It will remain 0 only. That is what you mean by this. Also, another thing is that if your voltage is constant, so which means if the voltage across a capacitor has become constant, as in DC, we can say that dV by dt will tend to 0. So if V is constant, then dV by dt is becoming 0, or which means current is 0. Current is 0 corresponds to an open circuit. So when we speak about the capacitance works like an open circuit to DC. Why? Because in DC voltage is constant, and hence dV by dt will be 0. So the current will be 0 through the capacitor. So this is about the properties of the capacitor. Okay, so what do you mean by initial conditions? Now, initial conditions are basically defined for circuits which have got inductors or capacitors. And why? Because why is it important is because these are energy storage elements. So when I'm speaking about inductors and capacitors, so I'm speaking about circuits where there could be some kind of an input. There is a switch, and there is, suppose I'm showing a resistance and inductance. Now, the switch is going to be closed at time t is equal to 0. So this means that the switch is going to be closed at time t is equal to 0. Now, since this circuit has got inductors, the inductance could have some stored energy in it before time t is equal to 0. So at time t is equal to 0, the switch is closed, which means that before that, your switch is open. So the conditions which exist before switching are called as 0 minus, and conditions after switching are called as denoted as 0 plus, which means what? At time t is equal to 0, some switching is taking place, right? So just before that, that time, just immediately before that, you call it as 0 minus conditions. So the currents and voltages which will be there will be denoted as I0 minus, V0 minus, etc. And just after switching, we call it as 0 plus. So 0 plus and V0, I0 plus and V0 plus. So these are called as initial conditions. And why are these very important? Why? Because inductors and capacitors are energy storage elements. They could have some energy stored in it. What is the initial energy which is stored in these elements? So initial current or voltage, which could be because of the stored charge, these could have some initial current or voltage, right? So these are expressed by the initial conditions, and that you find out. So those currents and voltages are denoted as 0 minus and 0 plus, depending upon whether the switches, we are referring to the time before the switch is changed, that is before time t is equal to 0, right? Just before switching, that is denoted by 0 minus, and after switching denoted by 0 plus. So this is what is about conditions. Now, initial conditions for resistor. Now, a resistor is an element through which the voltage and the current will change instantaneously. Now, suppose there is a circuit like this, and there is a switch, and there is a resistance. Now, at time t is equal to 0, so the resistance here is 2 ohms. Suppose this is a 5 volt. At time t is equal to 0, the switch is, before time t is equal to 0, the switch is open. The current through the resistance was 0. Now, at time t is equal to 0, the switch is closed. Immediately, the current becomes 5 by 2, which is 2.5 ampere, which means that the voltage and current are changing instantaneously for the resistor because the resistance has got a linear relationship. So, V is equal to I into R for the resistance, because of which the voltages and currents will change instantaneously. Now, it is not the same for the inductor. As the inductor current we cannot change instantaneously. So the inductor current cannot change instantaneously, and the condition before switching T0 minus will be the same immediately after switching. So if I say that there was a current initially flowing through an inductor, and we suddenly change the position of the switch, the current through the inductor cannot immediately change. We already saw that. We already discussed that V is equal to L di by dt. So sudden change means dt would be 0 or V would be infinity. So sudden changes are not possible, which means the current through the inductor before switching will be equal to the current through the inductor just after switching also. So if there was a 5 ampere current through the inductor, before switching, the same current would flow through the inductor just immediately after switching. Just after switching, it will not become 0 or whatever value. So I0, that is denoted by I0 minus is equal to I0 plus. So if there was initially there was no current, suppose there was through the inductor at T0 minus, then at T0 plus also the current would be 0, which means what? Inductor, if current is 0, you can say that the inductor will act like an open circuit. So again, so if suppose the current through the inductor was 0, there was no current flowing through the inductor initially, that is before closing the switch, then immediately after also that current cannot immediately change even if the switch is closed, which means that at time t is equal to 0 plus. So what is 0 plus? We already discussed this. Suppose this is t is equal to 0, and from here we start measuring the time, right? So from here, it's not the t is equal to 0 is the time when we are changing the position of the switch. It can be turned on or off, whatever, right? So just before that we have a 0 minus, and just after that we have something called as 0 plus. So the 0 plus is what happens just after switching. So if the inductor current was 0 before, then immediately after switching also it will not change instantaneously, so current remains 0. So that is what is defined by this equation. I0 minus is I0 plus. Now at the same time, if there was a current through the inductor, then the inductor would, the same current would flow through the inductor just after switching also, which means that the inductor can be regarded like a current source. So if there was a 5 ampere current flowing through the inductor before, then just after switching also the 5 ampere current would flow, or basically it can be considered to be working like a constant current source. Now, suppose we consider this example. Here, we have a condition where at time t is equal to 0, the switch is opened. So, which means that before the switch is opened, before time t is equal to 0, the switch was closed. So, now let us try to draw this circuit. So, before time t is equal to 0, the switch was closed and we had a circuit like this. Now, suppose I want to find out the initial current through the inductor, which is IL, right? So I have a 6 ohm resistance here, there is a 4 ohm resistance here, and this is a 10 volt voltage. So the switch was, we can see that the switch is getting open at time t is equal to 0. So before that the switch was closed, and this is our circuit. So at time t, so when you are before your time t is equal to 0, so which means suppose we call it a 0 minus, what do we say? So how do I find out the current through the inductor? Now this state where the switch is on, that is time before time t is equal to 0, we are assuming that this state has been on for a long time, so that the inductor has reached steady state. So we now already saw that if the inductor is in steady state, the voltage across the steady state means current has become constant. Whatever current it is become constant. So if I is constant, then V becomes 0, or your inductor V is equal to 0, which implies inductor will work like a short circuit, right? So we replace the inductor by a short circuit. So inductor, which is 5 Henry, replaced by short circuit. Then what do we get by a short circuit? So I redraw it like this. This is 6 ohm, the 10 volt source, and then we have this 4 ohm, and then I'm replacing the inductor with a short circuit. So the inductor has got some current, so we have to find out this current I. So what is the current? This current is going to be, now 4 and 6 are in parallel. So there will be a current which is, we can see that the voltage across this and this is same. So the 10 volt is across 4 ohm. The current through the 4 ohm will be equal to 10 by 4, which is 2.5 ampere. Or IL is nothing but 2.5 ampere. So this is the current which was flowing through the inductor just before the switch was open. So at time t is equal to 0, the switch is getting open. So before that, when the switch is closed, you have kept the switch closed for a long time so that the system has reached steady state. So once it is in steady state, the inductor you're going to be replacing by the short circuit and finding out the current through this. So you can see that it is the same current which flows through the 4 ohms since they are both in series. So the current will be equal to 10 divided by 4, which is 2.5 ampere, and this is nothing but your I0 minus. So I0 minus, IL0 minus is 2.5 ampere, and we know that once I open the switch, what happens? The source is removed now. But at the same time, we know that the inductor current cannot immediately change, which means IL0 plus is also. So the current does not immediately become 0. It remains the same for some time. So when you are opening the switch, at that time, the current is called as 0 plus, IL0 plus. It remains the same as IL0 minus Y, which we saw before, right? So IL0 plus is going to be 2.5 ampere. So this is the condition for the inductor. Now, when we speak about initial conditions for the capacitor, again, similarly, we can say as the capacitor voltage cannot change instantaneously. So this is what we say, capacitor, the change voltage across a capacitor cannot change instantaneously. So the condition before switching, T0 minus, will be the same immediately after switching, which is T0 plus. Or if there is no voltage across a capacitor, so basically we are saying that since your this we already discussed, I is equal to C dV by dt. So instantaneous change would imply that the current dt would be 0 or current would be infinity. So that is not possible, which means that whatever voltage was across the capacitance before, that would be the same voltage after also, which means at 0 minus, if you have like in the case of uh, before earlier case, we had a resistance and inductance. Here we have a resistance and capacitance, and at time t is equal to 0, we have suppose a switch is closed, right? So before that, if the capacitance had charged to some particular voltage, will be the same when you close the switch also, because instantaneous change in voltage is not possible. Or you can say that, in other words, we can say that V0 minus is equal to V0 plus. So if there was no voltage across the capacitance, like in this case, if the switch was open, after some time, the voltage, there is no source only, so the capacitance voltage will be equal to 0. So if I close the switch after some time, it will just start from 0. So capacitance has voltage 0. So if the voltage was 0, at 0 minus, then at 0 plus also the same voltage will be there across the capacitance. and if the capacitance is charged to voltage. So initially, if there was a voltage across the capacitance just before closing the switch, then just after closing the switch also, the capacitance will have the same voltage. Whatever it is, V0 minus will be equal to V0 plus, which implies that when a switching is happening, since instantaneous change cannot be possible for the capacitance, the voltage across the capacitance before switching will remain the same after switching also. After some time it will change, but just immediately after switching, the voltage remains same. So that is given by V0 plus. So again, as before, if we do this problem, in this case, again, the time at time t is equal to 0, the switch is getting open and the switch is closed at time t is equal to, before time t is equal to 0. So if I redraw the circuit, then the circuit looks like this. That is at 0 minus, if I say 0 minus is just before, here it is open just before opening the switch. So this is our condition. Now, since we have a capacitance here, what do we do here? This is 924 and the capacitance is 10 microfarad. Now we can see that the capacitance, when it has reached its steady state value, since I is equal to C dV by dt, and if it is a constant voltage, so if the we have kept the circuit on for a long time, the circuit that if this circuit is kept on for a long time, what will happen? The voltage across the capacitance becomes constant. dV by dt is 0 or current is 0. Current 0 means it becomes an open circuit. So the capacitor remains like an open circuit. So what will be the initial voltage across the capacitor? Obviously, the capacitance is going to charge up to this much voltage. So capacitance is connected across this 9 volt. So obviously the voltage across the capacitance V0 minus is going to be equal to 9 volt. So now when you turn off the switch, the capacitance will start from, so immediately after of turning off the switch, the capacitance voltage cannot change. So it will remain at 9 volt only. So this is what you mean by initial conditions. So these are due to the energy storage elements like inductors and capacitors, which store some energy, and because that is one thing, they store energy, and the voltages across a capacitor cannot change instantaneously. The current through the inductor also cannot change instantaneously. So because of which we have such equations: V0 minus is 9 volt. V0 minus is equal to V0 plus, that is in the case of capacitance, and I0 minus is equal to I0 plus for the inductance. Now, after speaking about initial conditions, we speak about final conditions also. Now, what are final conditions? Final conditions are nothing but steady state conditions. So once a circuit reaches steady state, we call it as final condition. So final conditions, so currents and voltages are basically reaching the steady state values. Now, for the inductor, we have V is equal to L into di by dt. We already saw this. So as the current reaches steady state, voltage becomes 0, or the inductor can be replaced by a short circuit. So this is what we were discussing and did it before also. Final conditions, you just assume that currents and voltages have reached constant values. For the inductor, we speak about the current, which becomes constant. So if the current becomes constant, the voltage across it is 0. V is equal to 0 is corresponding to a short circuit. Right? For the capacitor, I is equal to C dV by dt. So as the capacitor voltage reaches constant value, dV by dt is 0 or I becomes 0, which is that capacitor can be replaced by open circuit. So the net point, which is very important, is that under steady state conditions, your inductor can be replaced by, so replace inductors with short circuit. So final conditions are steady state conditions. Capacitance by open circuit. This is how you do. So this is very crucial that you understand this, use this when you are solving such problems. You replace the inductor with short circuit under final steady state conditions and capacitor with open circuit. Okay, so suppose we have a circuit something like this. So there is a 30 volt here, there is a resistance 10 ohm, and there is a 20 ohm, and there is a capacitance here Capacitance, let it be some 1 farad. Now, if there was a switch here and the resistance, time t is equal to 0, it is getting open. So let it be like this. So time t is equal to 0, the switch is getting open, right? Now, you are asked to find out V infinity, which means what? After time t is equal to 0. So, at time t is equal to 0, the switch is getting open. That means this part is getting open. And we are asked to find out V of infinity. Now, what is V of infinity? That is a steady state condition. Obviously, V infinity means time t is greater than 0. So, it happens after time t is equal to 0. So, at time t is equal to 0, the switch is getting open. And after that, you are going to be drawing. So the circuit can be drawn like this. After time t is equal to 0, our circuit will have 10 ohm, 20 ohm and only the capacitance here because the remaining part is cut off. So the capacitance, which is 1 farad, and this is a 30 volt source. Now, observing this, we know that what will be the voltage. So at infinity, which means steady state condition, capacitance can be replaced by a short circuit. So capacitance has to be replaced by open circuit at time is equal to infinity, which corresponds to nothing but steady state. So if capacitance is open circuit, then what will happen? The whole current will flow through, the whole current through the 30 volt source will go through 10 ohm and 20 ohm, which means current is 30 divided by 30, which is 1 ampere. And since the capacitance is connected across this 20 ohm, the current voltage across the 20 ohm will be current 1 ampere into 20. That means voltage across the capacitance is going to be equal to, so VC is going to be equal to 30 divided by 30, which is 1 ampere into 20. This is a 20 volt. So this is the voltage which will be V infinity is nothing but steady state value. Only under steady state we are going to be opening this capacitance. So what to find out infinity or the steady state conditions, what do? You see after time t is equal to 0, what happens? In this case, the switch is getting open. So after time t is equal to 0, whatever the system is, circuit is, redraw that. And once you redraw that, apply the steady state conditions, that capacitor tends to open circuit. If it's an inductor, we'll replace it by short circuit. So whatever it is, do the corresponding case and find out the voltage across the capacitor. Right. So this is about the final conditions. Again, if you see here, there is a switching happening at time t is equal to 0 and there is an inductor here. So here I can redraw the circuit. So I again find I infinity, which means I want to draw the circuit after time t is equal to 0. So the 6 ohm, 15 ohm, and you can see that the 6 ampere, 15 ohm, and the switch is getting close. So the switch is close and we have a 10 ohm and 20 ohm, these are in series. So I'll just show it as 30 ohm. And this is the inductor, which is a 5 Henry inductor. So 6 ampere current. Now, we can observe that at steady state. So infinity means what? Infinity is basically steady state condition and time after time t greater than 0. So at time t is equal to 0, the switch is closed, and at time t is equal to infinity, this circuit reaches steady state. So once it is in steady state, what do you do with the inductor? You replace the inductance with short circuit for steady state. Right. So for steady state condition, inductor has to be replaced by the short circuit. So we are finding out I infinity like this. So this the current through the inductor. So now if the inductor becomes a short circuit, the current, since it is in series with 30 ohm, the same current will flow through the inductor. Now how do I find it? The current 6 ampere comes here and split into this and this. So the current through the 30 ohm is the same as the current through the inductor, which you can calculate as, so IL is nothing but 6 into, we can see that these are two parallel resistances. So opposite resistance by the total resistance. So current through the 30 ohm, you can calculate it as 6 ampere into 15 divided by total resistance, which is 45. So 15 by 45 gives you 3, 6 by 3, 2 amperes. So IL is nothing but 2 amperes. So I of infinity, if you are asked to find out I of infinity, redraw the circuit for time t greater than 0, put steady state conditions to get the what the value of the inductor is. I mean, the inductor is replaced by the short circuit. then find out the current through the inductor using this, right? So these are called so to find out final conditions, we replace the circuit after time t is equal to 0. For initial conditions, you redraw the circuit for time t lesser than 0 or just before the switching is taking place. The switching can be either turning on or turning off, whatever it is. So before the switching is done, that is called as, and you find out initial conditions. So that is called as 0 minus, and you find out the initial conditions from that circuit. And similarly, for infinity or the final conditions, we use the circuit after time t is equal to 0. Redraw the circuit, use the steady state conditions to find the current. Okay, we can say to summarize that the current through the inductor cannot change instantaneously, or the voltage across the capacitance cannot change instantaneously. Now, this is the same thing. In other words, we can express mathematically as IL0 minus is equal to IL0 plus, or VC0 minus is equal to VC0 plus. So this what the 0 plus indicates that there is a switching happening at time t is equal to 0. Any switch can be opened or closed, whatever, in a circuit which has inductors. The current through the inductor cannot change instantaneously, which means just before opening the switch, whatever current flows will be the same current which is flowing through the inductor just after. So this is what is meant by this I0 minus is equal to I0 plus. For the capacitance, voltage cannot change instantaneously. So VC0 minus and VC0 plus will be the same. Now, under steady state condition, since inductor equation is given by V is equal to L di by dt, so we can write that inductor can be replaced by a short circuit under steady state conditions. When the current becomes constant, di by dt is 0 or voltage is 0, which implies that the inductor voltage, if the inductor voltage is 0, it is to be replaced by a short circuit. Similarly, for the capacitor equation is nothing but I is equal to C dV by dt. So, which means that voltage constant dV by dt becomes 0, current 0, current 0 corresponds to an open circuit. So, capacitors can be replaced by an open circuit and inductors can be replaced by short circuit under steady state conditions. So steady state conditions are also corresponding to time. We can also call them as that or the corresponding times as corresponding to infinity. So steady state condition means time corresponds to infinity. Initial conditions means time corresponds to 0. So this will be for the initial conditions, right? Initial, and this will be for the final. That is your time t tends to infinity, right? Okay, then. Thank you.